If you have a table with 1 billion rows, how many IOs does it take to query one row from that table? It's not a trick question. To answer this question, there are a couple of assumptions we need to make. So let's first assume we are querying using secondary index, and the secondary index uses B-tree. To make the discussion simpler, we want to restrict to point query only, meaning you are querying only one record. To make sure there's only one record being queried, we are saying, hey, this secondary index is unique. So you query by secondary index, you only get one row. So these are the assumptions. Let's pause for a second. What are your answers? If you have your answers now, that would definitely be wrong because we don't have enough information. So we gotta know, is it MySQL or is it Postgres? Because your table can be index-oriented or heap-oriented. If you don't understand what I'm talking about, that's okay. I'll explain it later. So with all these assumptions in mind, my answer to the question would be either 0, 1, 6, or 10. You're probably surprised by the answer 0. Well, because the way I set up this question is a little facetious, because if everything is cached in memory, there's no I/O. Maybe a better way of asking this question is, how many logical I/Os does it take to query one row? So when I say logical I/O, we are discounting cache. Nothing is in memory. If you want to query anything, you query from the disk. Okay, so that would make our answer more stable. So the answer would be either 6 or 10. The point of this exercise is actually to get our brain juices flowing and illustrate the point that index is not simple. There are a lot of nuances to the topic. But just to show you why the answer is 6 and 10, the number of IOs to traverse a B tree is log of n over log of b. So n is the number of rows, so in our case it's 1 billion. Now b is number of keys in one node. What does node mean in this context is one node is one page in a database. One page is about 8K or 16K depending on the configuration. It's good to use b as 100 as an estimate, meaning one database page can fit about 100 keys. Log 1 billion over log 100 is about 5. One B-tree traversal is 5 I/O. Then in the case of MySQL, you need 2 B-tree traversal, so you need 10 I/Os. For Postgres, you need 1 B-tree traversal plus 1 heap access, so that is 5 plus 1, that is 6. Here we are assuming that we need to fetch the entire row, meaning we are doing the select star. But if we are doing an index-only query, meaning the index already have the column that you want, for MySQL you only need 5 I/O. For Postgres, you don't need heap access anymore, that's also 5 I/O. The point of this exercise is really to show there are a lot of nuances to the topic of indexing. And I promise, by the end of the video, you are going to understand all about these nuances. Whether you're a beginner or intermediate, I'm going to explain all the underlying concepts in a simple and intuitive way. Without further ado, let's get started. Let's step back for a second and ask, what does the index do? Index orders your data. And when your data is ordered, it's faster to find a record. So that helps enforce uniqueness of your database and improve query performance. Speaking of the word data, index can exist as part of the data or separate from the data. Most of the time when we say data, we mean the actual records. Your rows with all the columns which you inserted. Usually we call that data. Depending on the database engine, the index itself may include that data. So that is the case for index-oriented table. There is a common database engine in MySQL called InnoDB. So all the rows which you inserted are ordered by the clustering key or the primary key. They are sorted on disk. And because of that, the index itself is the data. So we call these tables index-oriented table. There are other kinds of databases, like Postgres, where the data is actually not sorted, and the data, which is the actual records, and the index are stored physically separately. So the data section is called the heap. So the user inserted records with all the columns, they are not sorted. So they exist in one section called a heap, which is a Postgres terminology. And for the index are stored in a separate section. So that is one crucial difference between MySQL and Postgres. So just now I talked about the clustering index in MySQL. There's also secondary index in MySQL. So obviously secondary index are stored separately from the actual records. People say all the index in Postgres are secondary. That's kind of true, but the word secondary index is a very MySQL way of saying things. So I would just say there's just index in Postgres because there's only one type of index. What is index? Index can exist on the disk. So on the disk, we call it the index file. It can also exist in memory. In memory, the index is actually just the B tree data structure. So what is the life cycle of an index? Let's say initially your table is empty. You insert some records. We build the B tree in memory. We also serialize the B tree and write to the disk, which we call the index file. Let's say you shut down the database, you reboot. What database does is it load up the index file in memory into B tree data structure. So index file is really just the serialized version of the B tree data structure. Now the next question, why B tree? Why does index use B tree? The short answer is B tree is short and fat. That's why it minimizes I/O. Why does a short and fat B tree minimizes I/O? Well, to traverse any kind of tree, you start from the root. So you have the root node that's at the top. So you go from the root all the way down to the leaf node, that's where the data is. By the way, here when I say B tree, we are always talking about B plus tree. So the data, or rather the reference to the data, is at the leaf node. Later I'll clarify exactly what does the leaf node store. But here I just want to say, when you traverse from the root all the way to the leaf. So every node traversal, we call it one hop. And one hop is one I/O. So you think of it as, this is the root, you move your way down, that's one I/O. So you call it one hop. So you keep hopping down all the way until the leaf. Now leaf stores pointer to the record. Again, later I'll clarify exactly what does pointer mean, because depending on the kind of indexes you're talking about, the word pointer may mean different things. So I leave it purposely ambiguous here. Now, B tree is fat. So what does fat really mean? It means you have many keys per node. If you compare B tree with binary search tree, a binary search tree have one key per node, right? So that's like very thin. But when you store many keys per node, your tree is squashed. And so the tree is short. Hence, less distance from the root to the leaf. Less node to traverse. The path is shorter, right? So less I/O. And the realistic height of the B tree is about 5. Earlier in the video, I made a calculation. If you have 1 billion rows, so that means 1 billion keys, and you store in a B tree where every node stores approximately 100, so log 1 billion over log 100 is about 5. Now let's talk about what does pointer to the record mean. What exactly does leaf really store? So that really depends on types of indexes. There are three major types of indexes. Let's split by index-oriented or heap-oriented. A database engine like InnoDB is index-oriented. InnoDB is an engine in Mysql. I talked about it earlier briefly. It has the concept of clustered index, which is essentially the data itself. So clustered index stores all the rows with all the columns. And the rows are sorted by the clustering key, which is typically the primary key. So the data is ordered. Hence, index-oriented table. So for these kind of clustered index, what does the leaf node store? It stores the actual record with all the columns. When I talked to my colleague about this, they were shocked because they were like, the index stores the actual record, then how big is the index? Well, if you have 100 gigabytes of actual records, your clustered index will definitely be more than that. Hence, it can never fit in memory. Just let that sink in. Your clustered index is very big, bigger than the actual record. If your clustered index doesn't fit in memory, is that a problem? It's not a problem because part of the clustered index is saved in memory so that there's no I/O involved. Okay, so which part of the clustered index is cached in memory? You have a B tree which, let's say, is about 5 levels. Typically, the top 4 levels are cached in memory, so that when you traverse from the top all the way to the leaf, your first 4 hops are actually logical I/Os, so they are not real I/Os. So you only need to do 1 real I/O to the disk to reach the leaf. So it's not a problem that your cluster index doesn't fit in memory. Now let's move on to InnoDB secondary index. They are also sorted by the column that you specify. To make it simpler, let's not talk about composite index or multi-column index here. So let's just assume there's only 1 column. So what's the relationship between secondary index and clustered index? Obviously, they are not stored together at all. They are separate index files. Just to reiterate, for clustered index, the data and index are the same thing. They are bundled together. But for secondary index, that's not true. The index is kind of like a derivative data. Okay, so as far as the node traversal is concerned, it's the same. You go from the root all the way to the leaf. Now this is where the interesting thing is. What does your leaf node store in secondary index? It's actually the primary key. So you do not store the actual record. Now my question is, okay, I want to query a record using secondary index. I reached the leaf, I got primary key, then what else do I do? Now you need to do an indirection or a dereferencing, meaning, hey, I reached the end of my road, I need to go somewhere else. And where is the somewhere else is the clustered index. And this is where the answer 10 came from. If you still remember my answer previously, if you query by secondary index, in InnoDB it's possible to take 10 logical I/Os. Not real I/Os, they are logical. So we are assuming your secondary index B tree have 5 levels. Then you need to go and traverse the clustered index B tree, which is also 5 levels. So 5 plus 5 is 10. So that's where the 10 came from. Now let's talk about Postgres. Postgres is a heap-oriented table where the data section is called the heap and the index sits in the index section. So let's say you query some data using the index and you reach the leaf node of the index. What does the index store? It stores an internal ID from Postgres called tuple ID. Tuple ID is also called ctid or TID. Now this is the official documentation. ctid is the name of the column. It means tuple identifier or tuple ID. And TID is the type. It is a pair of numbers, the block number and the tuple index within the block. Okay, what is the block number? The block number is the page number. each page in Postgres is about 8K. So the block number identifies which page this data sits in. Then what is tuple index within the block? One block can store about 100 records, so there will be an index from 1 to 100. It identifies which record it is within the block. So with these two numbers, you know for every record which page it is, and within the page which record it is. If this is too abstract, let's walk through a real example. To make sure you really understand what the ctid mean, we can do some queries and see what does it look like. I have a table here. So the table is called T. It only have two columns. We have ID, which is the primary key, and we have pay, which is an integer. Just to hammer home the point that the Postgres primary key does not mean the same thing as InnoDB primary key, because the data in InnoDB are sorted according to the primary key. In Postgres, the data is not sorted. Only the index is sorted. We want to talk about ctid. When you do select star, just to see what it looks like, you can just add ctid, which is a system column from Postgres. There are other system columns as well, xmin, xmax for MVCC usage. I just want to show what ctid looks like. And it's really just a pair of numbers, right? 0 and 1. So 0 is the block number or the page number. And 1 is the item ID within the page. Okay, so how many items are there in the page? So we can find out. It can keep going all the way until 226. What that means is, hey, for my zeros block or my zeros page, there are 226 records. Then my page is filled up. Next record needs to go into the first page. So where does this 226 come from? This really depends on the page size as well as your table configuration. By default, a Postgres page is 8K. Now for the table, we only have two columns, both are integer, so that's very small. But you can have like 10 columns, and some of them can be string, can be double. So each record will take more size. So naturally, one page can fit less records. But nevertheless, a safe estimate is about 100. That's why previously when I did the calculation, if you still remember, log 1 billion over log 100, that 100 is the same concept as 226 here. So this is about how many keys can you fit per node. So the word node, block, and page really mean the same thing here. So I hope this demo helped you understand what is ctid. Now that we understand what is ctid, let's talk about what is heap access. Assuming you are querying from index, you reach a leaf node, you got ctid. With ctid, you know the physical location of the record, so you can do one IO to get the record from the heap. And that's really the primary difference between Postgres secondary index versus Mysql's secondary index, is that Postgres, we call it indirection, is one IO because we know the physical location of the row. But for InnoDB secondary index, your indirection is another B-tree traversal, which is potentially more expensive. ctid represents the physical location of the record. As long as the row's physical location changes, your ctid will change. And in Postgres, if you do a full vacuum, and if your vacuum operations leads to a lot of shuffling of the pages, that incurs a lot of cost. And if you compare this to InnoDB secondary index, primary key is independent of the physical location of the record. Hence, primary key is more stable than ctid. So you can say there's some design trade-off going on here. The fact that Postgres uses ctid, it speeds up the indirection, but it may incur some cost down the line. I hope this gives you a high-level overview of all the indexes available and their characteristics. So what's next? Just now we've only been talking about point query, meaning we are only querying one record. when it comes to range query, we need to think about random I/O because not all I/Os are created equal. We also have index-only query. We also have multi-column index, MVCC, isolation level. Speaking of isolation level, do you know that MySQL's default isolation level is repeatable read? But repeatable read, in theory, can have a problem called phantom read. But MySQL's InnoDB does not have phantom read. Why is that? Because there's MVCC. That being said, although InnoDB does not have phantom read, it has phantom write. Okay, so what is phantom write? So these are very interesting issues. We also have Postgres specific topics, vacuum, heap-only tuple, just to name a few. It's been such fun researching all these topics because I felt like I've learned so much. And I'm glad to share my learning journey with you. And with that, see you next time.